So I'm going to talk a little bit about Hilbert spaces, bracket notation, just to get you familiar with them. They're going to be used pretty commonly here in quantum computing. So first, I'm going to assume you have some knowledge of vectors, enough to know what an inner product is, and enough to know what vectors, to the extent of knowing that they're just an array of numbers with. I'll get more into the properties of the linear vector space just to summarize, but I can also direct you to some good resources if you need to brush up on that matter. But first off, I need to present the concept of linear vector space. A linear vector space is defined across a field. So the field could be the real numbers, or it could be the set of complex numbers. This field has certain properties, just your average commutativity, distributivity, associativity, the existence of zero, the existence of inverses, and that should get you pretty far with regards to just understanding what fields are in general. The reason why we abstract it to a field is because real values have that property instead of complex values, so it makes no sense to restrict ourselves. We could talk about more abstract fields as well, so we could, try to create a vector space out of, let's say, functions and make the inner product the integral, and you'll see that, especially if you go to continuous variable quantum computing. That's a little bit more of a common practice to do than this is. But linear vector space essentially generalizes this very familiar definition of that of fields to that of vectors, which are going to be things like A1 all the way to an. This defines the elements of the vector A. I should mention there's a difference between having these aligned this way and this way. I'll get there. I'll get to that a little bit later on. That distinction isn't necessarily so important in computer science or in mathematics itself or most applications, but it has an important distinction in higher level mathematics and just in more general. If you're going to treat this consistently, you must define this and this to give you a scalar if you multiply this by that, for example. So that's what we're going to call like an inner product. And if you do the math out, you realize that that happens to also equal the multiply each component of the two vectors, add them together. So it's going to give you an equivalent definition of your typical inner product. But an inner product actually, I'll get into that a little bit later. But so linear vector space, we have zero. That's great. Zero has a couple of defining properties. One is the fact that we add zero to any vector, we don't change that vector. So that's good. Another thing is we have A plus B is equal to B plus A. Geometrically, if I have a vector A and I have a vector B, it makes sense that, I'll call this, if I'm adding here, point to tail, head to tail, I get this point. This, if I go down B first and then along A, you would see I get to the same spot. It's, in some sense, if that wasn't true, it wouldn't make any sense. And so with the concept of zero. The main reason we need zero is this property right here, which is saying that if we have a vector v, there's something that undoes that. In the sense that if we wanted to get from this point to this point via a vector, we have a way of getting back. It really wouldn't make sense to say we don't have a way of getting back in most contexts, so that's just something to know. Another one is if I do, I can multiply it by a scalar and rescale the vector. So that can make one of these components longer, so that's how we get length. The relative difference in the values of the components is what defines your direction, if you're going to have a consistent sense of direction. So with that in mind, direction is determined by coefficients, and that determines essentially the angle and the magnitude of all of those mutually together to define the magnitude of your vector, because you need a magnitude and direction in order to define the vector properly. This is just saying that if I scale A by C, and then I add the scaling term C plus D together, that's the same thing as adding A scaled by C with D scaled by A. So now we also have this property, just the fact that we can associate it, U plus V plus K. I can do U plus V first, or I can do V plus K. The result will be the same. So that gives you a little bit of a definition of a linear vector space. A Hilbert space is nothing more than a linear vector space in the most usual of senses. So luckily for you, it's not much in the way of learning something new, as much as just assigning fancier terminology to something you should already be familiar with. Another thing I need to introduce is this idea of Euclidean norm. This is the norm you're used to, the square root of the sum of the components. So if I have, 1, 2 as my vector, it would be the square root of 1 squared plus 2 squared. So that would be just root 5, for example. But in the usual sense. I mean, this has some properties you may have not thought of, which is the fact that if we have a norm, we usually define, that's the magnitude. That's the inner product of a vector with itself. A norm is more generally a arbitrary sense of distance between two vectors, and taking the difference of components is what the norm in the Euclidean sense is. And that's why magnitude is defined to be the distance of a vector with itself, because it shouldn't vary in its direction, it should only vary in its magnitude. It's just a consistent way of trying to get an idea for distance from, within that same direction. And one thing about this inner product is the fact that it's symmetric, which, makes sense. I mean, if I go asking you, I go straight and then I turn left, what's my distance? It should be the same as if instead of taking a left, you took a right, if you're dealing with an orthogonal vector, right? If I travel the exact same distance, I travel the exact same distance. If you didn't have this symmetric nature, you would have, that wouldn't hold true arbitrarily, which is weird to imagine, but another thing too is that a inner product of a vector with itself only yields 0. In some sense, the magnitude is only 0 if you're dealing with a 0 vector. This has to do with the uniqueness of a 0 in a vector space, a consistent linear vector space. If that wasn't the case, you would have some weirdness, and you wouldn't have to. You could create a norm that obeys this. It's just you get some. I think this contradicts a couple of these properties that we're going to use later on. So, another thing is the fact that I switched my notation there. Oh, darn it. Basically, if I take an inner product with, let's say I take the inner product of x1 with this vector a x1 plus b x2. This is just going to be a, right? Because at some point, I don't care about the component along x2. I only compare that about x1. Definitionally, that's a. Because for inner product, I can take out constant scalars. So I would take out a, and then I have the inner product of a vector with itself, which is 1, definitionally. Now this is saying that mathematically it's the same thing as if I took a, then the inner product itself, then I ended with b, and this inner product of x2 and x1. Which, makes sense. The only reason why I knew how to handle this was because I was implicitly assuming this to be true, based on just what I knew this vector to be. But that argument happens in general. The fact that I described this across the basis of x1 and x2 made it easy to see that, but in general, we would like to have this decomposition in case that doesn't necessarily hold. So that gives us a little bit of our excursion to Hilbert spaces. Kiskit's textbook does a good job at explaining them. I'll do a couple of examples just generally of working with this, but what we say in quantum computing is the fact that we're dealing with a Hilbert space. That onto more of the semantic notation of things, we're going to be using something called a bra-ket notation. A bra is just this right here, it's this object, and a ket is this object. So now, what do they actually look like, right? Because at the end of the day, this is just fancy symbols. What does it actually look like? A ket is just your normal vector v, essentially, in the way that you probably know it, which is, it's just v1 to vn. And then we have our bra. So I'm just this is how I would denote that. This will be denoted in the opposite manner, or pointing to the left. So this one, this is going to be row vector instead of a column vector, v1 to vn. And the question is, well, how do I remember why it's called bra and ket? Well, in some sense, you can think of these as brackets, right? So if I literally do a bra ket, what I'm actually doing is I'm finding an inner product And I'll show you why that is. If I have this v1 and v2, and I dot it with v1, v2, I get v1 squared plus v2 squared, which is close to what the inner product would be. We can define this as an inverted of that if we want to, but in some sense that we only care about the relationships of how the norms change with respect to each other. It's an important thing to note that if I scale my norm by 2, it is exactly the same. It uses the same linear vector space, same transformations. It's just as if we decided to make our primitive ruler a different size. So in that sense, it should make sense that, and also, rotations of our norm. So if we change our basis, our norm should still be consistent. The idea of distance shouldn't change. But this is bracket, just fancy way of representing it because we don't want to draw those big ass vectors all the time with those dots. Unitary. This is a property about all transformations, all gates, the x gate, the z gate, I'll get into the gates a little bit later on, but if it's a gate, it's unitary. That means if I apply it again, I get its inverse because its conjugate is its own inverse. Well, in this case, I think Hermitian it's equal to its complex transpose, not for unitary, my mistake. We have this idea of its conjugate, so its conjugate itself always cancel out. However, for the polygates, they're also their own inverses. Unitary, the reason why it's called unitary is because it preserves the unit distance. So if I have a vector, which is normalized, n, and I were to apply u to n, this is going to equal n when I consider the norm. So, n is a unit direction, preserves it. And that's what this property more generally is, because if you think about it, if the individual distances of vectors don't change relationally, they don't scale, and you have a linear vector space, you could add half of v to half of v. And then the cool thing too is we can rotate v and it shouldn't change a metric, right? So in that case, we have this arbitrary thing that ux and uy should equal x and y. You can prove that out mathematically. It's a good exercise for like a 2x2 unitary matrix. I might wonder what's the form of a unitary matrix? Well, it has real eigenvalues. Its determinant is equal to 1. That's the other thing about the determinant. What the determinant actually is it's the area or volume or higher dimensional conception of volume after you so you take your basis vectors, v1, v2, I act with u, and this would be, for example, saying that this area is equal to that area, would be me saying the determinant is equal to 1. So you can see why the determinant equals 1 kind of follows for that. And very, 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 very unobvious things, the fact that it's diagonalizable and it has real eigenvalues. Diagonalizable means we can assume that we can convert into a basis in which any operator is just a diagonal matrix. So if you ever try to take a to the n, you probably did this trick before where you convert your basis so that a is diagonal. So a d diagonal, a diagonal, take that to the power of n because that's easy because that's just the just take n to the diagonals. And that's it. That's what it is. Then you have basis from and basis to. It's a you do a active transformation of your vector space into the eigenspace it's called, or the eigenbasis, and then you get out of that to get the same thing. That's just a trick we use commonly when trying to show that, if we apply, let's say, Grover's algorithm n times, because Grover's algorithm is just two matrices multiplied together, so it's another matrix, and its application n times is the same thing as a to the n to the initial vector. So if we want to prove things like convergence and all that, we need to actually work with the diagonalized form of the matrix. So the fact that it's diagonalizable gives, one, it would be impossible to do analysis otherwise, or near impossible. Another thing is I'm going to introduce this idea of a Hermitian matrix, which is the fact that A is equal to A complex transpose, or A dagger. You might wonder, what is A dagger? A dagger is the same thing as A transpose, and then take the complex conjugate, which is if you find an I anywhere, just multiply by -1. So just change I and just replace it with -I, and simplify, and that'll be the same thing. Now, an immediately obvious thing should be the fact that it doesn't matter the order in which I do a transpose in the conjugate, doesn't change anything. Should get the same result. That's true. So there's no disambiguity when we use this symbol on what operations meant. The two interpretations happen to be equal to each other, which is convenient. This has real eigenvalues. Unitary matrices have this desirable property that they can be thought of as a complex exponentiation of a Hermitian matrix. And that implies some things about Hermitian matrices, such as the fact that they also have real eigenvalues. The reason why Hermitian matrices tend to be observations, it makes sense if we don't have a complex value for things like position or momentum. That leads me to some other things, but this is kind of the mathematical lying underpinning of quantum computing. As you can see, it's nothing too distant and far off land and enigma, but as you probably saw with the amount of notation introduced and just these fancy terms I'm throwing around just so haphazardly, it can be intimidating, but it's at the end of the day, it's just basic linear algebra, just wrapped up in fancier form, so mathematicians can feel better that they're working with pretty simple things. So now, when I talked about gates, gates are important. There's the X gate, there's the identity gate, which is in our case equal to the Z gate, and then there's the Y gate. Actually, it's not equal in our case. The measurement on the Z basis is the same thing, but we have the Y gate. These are our most primitive ones, and then I'm going to include this, which is our controlled knot. Yeah, so that's what I'm going to start off with. It's just these are, I'll do a phase gate, P gate. Alrighty, so X, Y, Z, and identity. These form a set. If I have a density, okay, I won't go on what a density matrix is. If I have matrix A that is Hermitian, I can decompose it as A times the identity plus B times an X gate plus C times the Y gate plus D times the Z gate. So you're going to run into that from time to time, usually in research papers, just because this mathematically is a lot easier to work with, a linear combination of X, Y, and Z, just because X, Y, and Z are so well studied. And the identity matrix is that's the definition of being well studied. Based on the fact that we can understand almost every matrice's operation as X, Y, and Z, actually has more of a deeper meaning than just the fact that it makes our interpretation of our algorithms easier. It also makes the execution of these algorithms a lot easier as well, because this may seem like we're defining the space of all transformations and X, Y, and Z. These things are orthogonal to each other is what this implication is. It almost looks like it's forming a basis, and it is forming a basis. We can actually define that basis of the component of the one, of the identity matrix, the X matrix, the Y matrix, and the Z matrix. And we can just say that's what matrix A is equal to by definition. Okay, X gate, what is this? X gate is the NOT gate. So just very fancy for an X, but it's basically not whatever it currently is. So the 0 vector changes to 1, and the 1 vector changes to 0. And I should mention something. The 0 vector here is not the same as the 0 vector I mentioned before for the vector space. It's just because we want to use the same thing as normal computing, so we want 0 and 1. So I'll define what 0 and 1 is at the moment. 0 is going to be this, 1, 0, and 1 is going to be its opposite, 0, 1. I should also mention, what can an arbitrary vector be Well, in this case, it can be, A plus BI, C plus DI, with some constraints on A, B, C, and D that I'll get to later. But the X gate, it does that. You can kind of assume what the matrix would be because of this. I can literally just say 2 from, so this should be 0, 1, 1, 0. The identity is pretty just your normal identity matrix, 1 in the diagonals. Okay. A Y gate, a Z gate, in some sense, it changes phase, but it's just identity with the second one being a negative. And then the Y gate is kind of very much like a Z gate, except we do so with I. Now you might wonder, couldn't I have chosen to do this in a different way, put the i's, more similar to x? Yes, you could have. The main thing is these matrices remain orthogonal to each other. So those are the transformations for these. Now, this doesn't really help that much because we need to understand what a qubit is, right? So these are the operations that apply to it. My mere point of mentioning x and y and z is the fact that underlyingly these are vectors and these are matrices, and that's all we're ever doing. We're just doing matrix multiplication. It doesn't get more complex than that. The analysis might just in arguing about things converging and stuff like that, but at the end of the day, it sounds a lot more complicated than it is. This is usually what we call a circuit diagram. So this would denote, we always assume things are initialized to 0. If we want to initialize something for 1, we usually just apply the X gate. It's just implied that the fact that this is going to be 1 now, just common knowledge. And then I can do something like this, which is, this is saying control, and this is saying not gates. And this is our 2-qubit gate. This is how we're going to get qubits to interact with each other. So this is 1, so it flips this one to 1. And that's how we get conditional logic. Now, another thing about unitary matrices is the fact that they imply, because U's inverse is going to be equal to U conjugated, we have this interesting property, which is the fact that quantum computing must be reversible. Whatever computation is done must be undoable. The only thing to the exception of that is measurement. Once we do measurement, we can't undo measurement. This is some weirdness that you're probably not acquainted with, but I'll explain a little bit. So I have this is going to be called our block sphere. It's literally a sphere. The one pole is going to be 0, bottom pole is going to be 1, and then we can describe our current position or current superposition of 0 and 1 as being on this sphere. And you might be, well, why? Well, I said before we can represent it like this, that, let's say this is alpha, right? Alpha, I can choose 0 and 1 as my basis, right? That's implicitly what that vector is implying. And then I can just do this. Just stating explicitly what the components of that vector is. Now, another thing is the fact that at the end of the day, when we measure, we either measure 0 or 1. This is the unfortunate reality of quantum computing. If we could measure more than that, we would have something that can solve NP-complete problems. So, rather interesting that we can't, unfortunately, but c'est la vie. So is the way of life. One thing about it as well is the fact that we only measure whether or not we got 0 or 1. We don't measure how much we got 0 or how much we got 1. That would be having way too much information. So what that implies is that we have to be normalized. So we have to be able to say that A plus BI squared plus C plus DI squared, this has to be equal to 1. This is one equation that constrains one of these values, right? So we have a three-dimensional object. We say that D can be determined as a function of A, B, and C due to the constraint that it's unitary. So this implies we're dealing with a 3D space. We have 0 and 1. This is kind of like the closer we are to one of the poles, the more you can think we're in that direction of the closest pole. That's an interpretation. Now it should be pretty apparent. How do I make a uniform super? How do I make it so that it's a 50-50 probability of being in 0 and 1? Well, I have to be on this, the equator, right? That's the case. Now, the equator, well, I can just say 1 over root 2, 0 plus 1. And that's because I said before the probability of, measuring a 1, so the probability of 1 is going to be our vector. Its inner product with the other, and I said the inner product before is the following Brock-Kett notation. I can say 1 and inner product with alpha, and I can just take it, this squared, and that would give me the same thing. I just take the magnitude of the inner product and I square it. And this, I square this, we get half and half. Now, there's another thing that this kind of implies, which is the fact that we can factor out, as I said, we can only measure magnitudes, right? We can only measure the probabilities, the expectation of the probabilities. That's the only thing we can ever measure. So because of that, what if I pulled out a common factor, e to the I theta? I can do that. There's no harm in doing that. That's what we call global phase. Now, how do we get the sphere, right? The circle, I mean, the circle of things that we can be in. Well, it can't be global, because we can factor that out, right? So it has to be between this x1, this 0, and this 1. So we can do e to the I, phi in this case, 1. Phi can be negative. Phi can be like an angle. You can think of it as the angle. So like you can just say right here is, 50-50 superposition. It's somewhere. Let's just say it's there, because this is going to be positive x and positive y. Or maybe it'd make more sense to put it right here even, just 45-45 in the positive x and y direction here. We can think of the 4 possibilities of changing the sign as being these, and then our angle as being phi relative to this xy intersection there. So that's a little bit about the block sphere. It's just a tool for visualizing our superposition. It's just the sphere that we use. Now why do I mention it more particularly is because we can imagine these x, y, and z gates as being rotations on our block sphere. So the x-axis, if I have, I'm saying I'm in 0. If I want to switch it so that this thing's 1, I have to rotate along this axis right here. So this is our x gates axis of rotation. We rotate right here. We just flip it, and how much do we rotate by? Well, we need to change it by 90 degrees, so it's a 90-degree rotation. The z gate needs to be a rotation such that it doesn't change. It's basically an identity matrix, right? It just changes a relative phase between 0 and 1. So it has to be right here. So this is going to be our z, and then that leaves us here with our y gate as being a 90-degree rotation across this axis. And our true identity, z doesn't change measurement, but when you interact things with each other, you can actually get that negative sign to matter. That's why we have negative signs. That's why we need to take probability squared, because we can't have negative probability. Why do we have negatives? It's because in quantum mechanics you can have interference. So certain possibilities, you can act with an operator and they can cancel out other possibilities. So that's all that rays need to be known about this. This is called superposition, the fact that it can be in, somewhat a 0 state and somewhat a 1 state. Entanglement is the fact that, I'll go into a little bit of that. We can define something called Bell states. I'll go a little bit into Bell states now. What is a Bell state? So if I have, they're essentially just uniform superpositions in which two qubits, and this is how I denote multiple qubits. 0, 0 can be written as just 0, 0 together in the ket, or yes, in the ket. So if I have, ones, zeros, a normalized root 2, that's 1. 2, what if I had a negative sign between them? Completely possible, doesn't really change anything. Root 2. These form a basis for all the possibilities between these two. Free, I can also do the same thing, but this time just have I right there. I can do the same thing, but have negative I. So all these, you might see, usually don't see these negative signs. Usually we just take the positive ones and just apply, your typical Z gate, or your, whatever gate you need to, and create that signage. But then you can also do something a little bit different, which is maybe they oppose each other instead of always being the same. And then the others are just similar variants. These are the Bell states. This is entanglement, because if you think about it, there's nothing classically that it means that if I were to measure one of them, I instantly know what the other one is if I know it's prepared in a Bell state, or a certain Bell state. That's very powerful information to know. The fact that, now classically it doesn't have much of a analog, right? I mean, if I have two objects, even if they're perfectly identical to each other in production, I mean, who's to say you haven't messed around with the other one? But the main thing about this is if I mess around with one, I mess around with the other. Definitionally, I can't apply one operation to one of them to separate it into something I now know nothing about. Now, so that's something the Bell state. This is entanglement. Things just aren't that correlated because now we can't consider them independently. We have to consider them in combination. So, in some sense, what does that mathematically mean? How do we treat this? Well, if I have A, I have B, I take something called the tensor product. And this one, I'm going to say A, B, and just let A and B be complex valued, right? This one, C and D. What this is, it's all possible, because there's 4 possible combinations of this, right? 0, 0, 0, 1, 1, 0, and 1, 1. We say this is AC, AD, BC, and BD. Corresponding, instead of just 0 and 1, to now 0, 0, 0, 1, 1, 0, 1, 1. And if you think about it in probability, it makes sense we should be multiplying the components in this way. Now, and this we can specify as AB is the common notation to use. If it's, A and B are just zeros and ones. The Bell state, let's see. What else do I want to mention? We can do this with operators as well. So if I apply x to 1 and x to 2, we can denote it like this, where the subscript denotes, what we're doing. And then let's say, I take this and I apply y gate to 1 and a z gate to 2. How can I mathematically represent this? Well, let's consider x1 and x2. This one, when we take two qubits together, we take them from top to bottom. So if we have a whole register of them, top one is the 0th one by convention. Same thing here. We apply, it doesn't matter in this case because applying 1, x to 1, and x then to 2, or 2 then to 1, they're separate things at the moment. They're not entangled. It doesn't matter. They commute. That's called. But I can do x1, x2. We just usually do it so it's the same ordering as the qubits, so top to bottom, or in this case, least significant qubit to most significant qubit. So this is x commuted with x, or x tensored with x. We can just do this out. So 0, 1, 1, 0, tensored out with 0, 1, 1, 0. And this you might be like, well, what's generalization here? Well, I can just take this matrix and put in these components and multiply it by these correlation, coefficients. So first one, 0, 0, 0, 0, and this one's going to be 0, 1, 1, 0. This one's going to be 0, 1, 1, 0, and then 0, 0, 0, 0. In some sense, you can see how it has this block form to it, where it looks like a local operator, in both the large sense and the small sense, which is kind of what we wanted. Well, we can apply that matrix now to, the tensored version. And, where does quantum computing get its power from? That's the one thing that I should discuss now, which is, normally with computation, we take x, we apply u of f, which is just a function, to x, and we get our y, our output, or f of x. And this is all computation is. Nothing fancier than that. So where does the quantum weirdness come about? Well, the issue is this right here, the x. X is kind of limiting. You can only try one thing at once. We can only apply f once. Maybe f is efficient to do, but trying out every single possible x slows this down. So I'm going to introduce Grover's algorithm to give a little bit of a suggestion for how this might be useful. So I start off with all zeros. I have n qubits. And I'm looking for an n-bit solution. So let's just say that's going to be all ones. 1, yada, 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 1. First thing I gotta do, well, if I don't want to try everything all at once, I have to be in a superposition of everything, right? And everything, for each qubit, I should be equal probability 0 and equal probability 1. Well, we can apply the Hadamard gate, which is a 45-degree rotation instead of a 90-degree rotation. So it's like a NOT gate, but it's like half of a NOT gate. So that's our Hadamard gate. I think it should also change the space, so maybe not truly the square root of x, maybe it's I times the square root of x matrix. I have to check that. But, why make this more complicated? Just a bunch of Hadamards. That puts us in a uniform superposition. So instead of being from all zeros, now we're in a state of, now if we say this is a binary number denoting 0, we can let I start with 0 and be 2 to the n minus 1, right? Those 2 to the n possibilities, and say I. And this has to, probabilistically, we have to sum to 1, so each of these is going to be I, 1 we square it, so I 2 to the n. This is what our new state is, okay? So this is pretty powerful now, because what if I applied f of x to this? Well, by definition, I get 1 root 2 to the n, summation of I equals 0, 2 to the n minus 1, or not minus 1. And I have, in this case, f of I. But if I try to measure now, I'm a little shit out of luck, ain't I? Because I only get one of these possibilities of f of I. Okay, that doesn't sound like a great solution to me, now does it? We need to do more than this. So, if I'm dealing with 3D space, okay? I have something that's A, B, and 0. So in this case, if I draw this out, this is our xy plane right here, x, y, and z. This vector is just somewhere here, right? Denoted by A and B, okay? I have a vector here that's z. Don't care how much, it's direction c along z. So it's 0, 0, c. These things are orthogonal to each other, right? Definitionally, because it has no component of the other. Well, in this case, we have to consider, when we have n qubits together, all possibilities, right? So we're dealing with a 2 to the n dimensional vector space. So, our solution is just one of these. Let's say it's I is our solution. And everything else, 0, let's say I is not equal to 0, just to make my life easier. I, and it's not equal to 2 to the n. All yada yada yada, alpha delta I. So this is going to be I minus 1, that's going to be I plus 1, it's going to skip I, and go all the way up to 2 to the n, right there. So this is all of our solutions this is what we want. We're saying there's only one unique solution, I, and this is what we don't. Well, I can draw that out, right? Because both of these are vectors. I can just sum this, be uniform. We're going to say this is W orthogonal, and this is W. So if we're in a uniform superposition, we're mostly along this W perpendicular, right? So this is where we are now. This is our S, or superposition. Unfortunately, our component right here is only 1 divided by 2 to the n minus 1, because we have one less combination. And this is, everything else. So this is basically 1, just 1 minus 1 over root 2 to the n minus 1. Oh boy, that seems like a bit of an issue. We're unlikely, if we were just to randomly sample, to get our solution. That makes sense, right? We don't know what our input is, essentially. So the chances of us just randomly guessing is 1 over 2 to the n. Not better than classical. So I'm going to introduce this idea of an oracle. And what it's going to do is it's going to rotate this by 2 theta, where this is theta, to negative s. You might be like, what do you mean by negative s? Well, in this case, what does negative mean? It means that we change w, so its projection is now negative. So we need to mark with a relative phase our solution w, somehow. Somehow, some way. Now, I said we have a way of knowing which one's the correct solution, right? I don't care how complicated this is, it's u of f, it's a function I can apply. And let's just say I do a NOT gate if and only if this turned out to be true. So now this is, there's 2 possibilities. We are looking at, our solution. So this is 1 if we're looking at our solution. Else it's 0. So it's going to be 0 most of the time. What we can do now is we can take just one of the qubits and we can change it so it has a phase gate. And this is going to do that relative phase. We're going to control only, we're only going to apply that if this one is 1. So if I take this phase gate and I apply it, there you go. Well, now you might say, like, oh, Dylan, I think you messed up everything by applying u of f. Yeah, you're probably right. I probably did. Luckily for us, we can undo that pretty easily. We just need to apply. Nice thing about this, quantum computing is reversible. Just need to apply this. And this one, what do we do with this right here, this 0? Well, we don't need to do anything along with that. We don't actually care what that value is, so it doesn't matter to us. But we just need 1 qubit. And you can see how this just only puts a negative sign on those components along those directions which happen to be 1 when u of f is applied. It's what we want. It rotates it. So now, I won't go into the gate decomposition of this. But let me go, we have W, negative W, we had our S, and we had our W orthogonal. Now we have successfully rotated it. So this is in total 2 theta. So now we're at negative s. Well, not negative s, but negative s for the negative for the component that we want. So let's say I is w as our solution. Now, this doesn't really give us a good indication of what the next step is. Instead, let's look at another visualization here. This is going to be all zeros. This is going to be all ones. Our solution is all ones, right? Initially started out with this. Now we applied a negative sign. So, if I move this along, what does this look like in this picture? Well, it looks like I rotated this from positive to negative. You might be saying, okay, Dylan, that's great and all. What did that do for us? Well, now, the average was once here. The average is now here, because one of the values is negative. What if we did a rotation on the average? We rotate this, this goes higher. These go lower, because they're above this average, and this is below the average, but negative. So mathematically, what is that? Rotate amongst a specific axis. Well, we can take the identity, minus by 2, the projection operator, which is, in this case, this is just the outer product. So in this case, you know, instead of, it's this basically versus this. One, you get a matrix, one, you get a scalar. But it has a property that if I were to apply, you know, S to anything that, you know, anything else, K, or S is not equal to K, let's see what happens. Well, the projection of S to K, they're orthogonal, so they're 0, right? 0 component of S, we get 0. That's great, it doesn't do anything. What if we had S? Well, the inner product of S and S is 1, so we get S. Great. How does it help us? Well, let's look at what this thing does. We apply this thing to our input, and it has some component that's S, you know, so 1 over 2 to the n, and it has literally everything else. We don't care. This part is not going to give us S, so we're just going to get identity. But this part is going to, no, actually, this one's actually going to subtract a little bit. Take that over. Whoop. Anyway, let's apply it to these two cases. Let's apply it to S. In this case, what do we get? We get, well, first we get S. Then we get 2S. So we get minus S. Now we apply it to everything else. We don't get this component, so we just get K. So that's essentially what our operation is going to be. It's a rotation amongst the axis of S, or our desired solution. Or all of S in this case. Our uniform superposition. And if you think about it, that should have been the average before, right? Or the average rotation along the current, the prior S is a rotation of that. Let me actually draw this out here so I don't sound so weird about this. We got this, which is negative S. Well, not negative S, but S with a negative S2. And this is S1. Let's do that. This is negative W. This is W. This is W orthogonal. So all that really needed to be shown previously was the fact that we act differently towards our value of S or value not of S. Oh, that. So what happens here is we end up going negative. We're negative and negative. Where does it go? It's positive. We still had S, right? We still had identity, so the projection gave us S again, so we double our value of S. So we get closer, twice as close as we were. So this is theta, theta, theta. This is this to this is 2 theta. We rather rotate uniformly up to theta from that. And the question is, how many times do we need to do this? It's a geometric exercise, but the running time of this is about pi divided by 4 root n. So it's about square root of n. Where n is 2 to the lowercase n. N is just the number of states. So if we add in bits, it's 2 to the n. Which, you know, is still not incredibly fast. It's the root of an exponential versus the exponential itself. But it's a lot faster than you think we could you should think we can do without giving, because we didn't know anything about f, right? We didn't exploit the property of f at all. We just said, hey, let's just try to find a solution. So that's a little bit about Grover's algorithm and a little bit of how we might do analysis. So that explanation is actually quite modern. It didn't exist a couple of years ago. So you can see how, especially for this later stuff, the formalism might be very math heavy. And you might be like, oh my god, I hate this. Rightfully so. But the thing that you shouldn't be concerned with is the fact that you should note is that we're getting better at explaining it. People are learning how to teach it. They're better understanding how these algorithms work. So the explanations are getting better. So, but we're not completely at that period in which everything's easily explained. So at the moment, it's a little enigmas, and that's kind of what this project's purpose is for. It's to create a tool for people to learn more about quantum computing. So essentially, we're accepting the fact that the current explanations aren't excellent, and we're looking to improve that. So we're willing to help you guys learn more about quantum computing. If you guys are reading a research paper, I'll try to best my ability. Luckily, we seem to have an interested professor that's willing to, show us how it goes. So if there's something I don't know, that's another resource that we could reach out to. So, yeah, that's a little bit about Hilbert space, block sphere, and Grover's algorithm. And I think that's enough for the first lecture. I'll cover Shor's and go about simulation and taking eigenvalues and eigenvectors and eigenbases and stuff like that a little bit later on. I think that was certainly enough to digest, at least for the current period. So I'll let you be.